In this video, I'm going to try something a little different. I'm not really, all of my other videos have been completely scripted, and I'm not really good at sort of ad-libbing and doing kind of what Ken does, getting in front of a camera and just talking. I'd like to be more like that, but I'm not. And so I'm going to give it a try and see how this goes. So this video is going to be about the Mandelbrot set. The Mandelbrot set is my, area of expertise. I have been programming it and studying it since around 1985. And I think this is an important part of my cosmology. In fact, it is the most important part of my cosmology and the fractal paradigm, the fractal cosmology that I am, trying to promote. So what do fractals have to do with magnetism? That's a really good and important thing I ask quite often. And so, magnets are, well, self-similarity is actually one of the major features of the fractal cosmology, of the fractal paradigm. And magnets have the property of self-similarity in that when you break a magnet in half, you get two magnets that are self-similar to the original magnet. And if you break those magnets in half, you end up with four magnets that are self-similar to the original magnet. And so self-similarity and magnetism are very similar to the fractal paradigm. And the fact that the hypertrochoid pattern that you see under the ferrocell creates a phi spiral, and phi spirals are a ubiquitous feature of the fractal paradigm. And so what I'm going to do is I'm just going to show you a bit of software that I've written on the Mandelbrot set, and I'm going to try to give you a better idea of what it is and how it works and why I think it is so important. Okay, so here is a version of my software. I wrote this, I don't know, 10 years ago or more, probably more. So this software is the software I use for generating pretty pictures. So basically, here's the Mandelbrot set. And the Mandelbrot set literally lives in the complex plane. This is literally a picture of the complex plane. Now, you might remember from a previous video, I showed you, I showed you how complex numbers are two-dimensional numbers, and because complex numbers are two-dimensional numbers, they can be housed in a 2x2 matrix. So this is one example of a complex number where the real component is on the forward diagonal and the imaginary component is on the backward diagonal. And you will notice that the real component has the same sense. In this example, both the real components are positive and the imaginary components have the opposite sense. And so the imaginary component has a positive and a negative in the backward diagonal. And so there are four, I call them flavors, there are four flavors of these. One is with positive, 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 negative, positive, positive, negative, positive. So you'll notice that the imaginary component was flipped in this version. Okay, and then you have the negative real. So you can have negative real in the positive component and positive negative or negative positive. Now when positive, negative, and negative positive, these are complex conjugates. In standard terminology, they call it the complex conjugate. And the complex conjugate is just a flip of the imaginary component about the real component. So in this case, if you flip the imaginary component about the real diagonal, you end up with the inverse. And so these are the four flavors of complex numbers, which correspond to the four quadrants of the Mandelbrot set, which literally lives in the complex plane. So the real component is the vertical component in this case, and the imaginary component is the horizontal component. And the main reason why I put the real component vertical and the imaginary component horizontal is because I like it this way. I like the left-right symmetry. I like the sort of organic, Buddha-like structure of this orientation. It's completely arbitrary which way you do it. If I put real on the horizontal, then this would be tilted 90 degrees. So I could easily do that, right? If I want to rotate 90 degrees, okay, it's going to look like that. And when you look up the literature, they almost always have it in this orientation, but it is completely arbitrary, and so I prefer it in this orientation. The other thing I want to talk about is my Mandelbrot set as a quasi-black hole theory, which I'm just going to briefly mention because this is really the basis of my cosmology. Yes, relativistic black holes don't exist. I agree with that 100%. Okay, but the Mandelbrot set has a lot of features of a black hole, and so this is the black hole of the standard Schwarzschild black hole, which is very simplistic, and this is the my black hole model, which has an event horizon that is infinitely long. So the event horizon of a Schwarzschild black hole is a circle or a sphere, and the event horizon of a quasi-black hole is an infinite fractal curve, and all the interesting stuff happens at this infinite fractal curve, and that's what I would like to show you. So basically, so what this program does is when you click on a point in the complex plane, it zooms in to that point. And as I'm zooming in, what's happening is the measuring stick, which in this case is the pixel, is shrinking. Okay, so each time I zoom in, I'm actually shrinking the pixel so I can get more resolution. Okay, so each time I zoom in, I'm shrinking the measuring stick and I'm getting more detail. So as you can see, we can zoom in many times and see similar features. Okay, and the really cool thing about this is, like, eventually you always find more little Mandelbrots. Okay, not to mention the fact that the pictures are very beautiful. Okay, so what's going on here? Okay, I'm going to reset again back to the original, and so what you're seeing here is a far away from this horizon, which I'm calling an event horizon. And you know, it's sort of, you see like this gradient pattern. Okay, there's a gradient being formed, and we'll talk more about that later. And on the inside, you don't really see anything. It's just black. It's arbitrarily painted black. I could paint it blue or red or green, but these are the points that never escape the event horizon, no matter how many iterations I make. Okay, so the inside points never escape, and the outside points always escape. And if you read my paper, you'll see how I connect this to black holes. I'm not going to get into that too much here, but that's basically why I think it's a black hole, because the points on the inside behave like singularities, and the points on the outside behave like the photon sphere of a black hole. But I'm more interested in the event horizon, because the event horizon is where all the pretty pictures come from. Okay, so every time I click, I can zoom into a new region, and each new region looks very different than previous regions. And no matter where I click, I can zoom in on there, and every once in a while you find another Mandelbrot. And those little Mandelbrots appear in very specific locations. Okay, I'm going to show you how to find them. Okay, so as you zoom in, I'm going to zoom into a little region here. Okay, whenever you see a bifurcation point, and what I mean by that is whenever you see sort of something going this way and something going that way and something in between, then you will find a little brot, Buddha-brot, Mandelbrot. Okay, but if you zoom in, say in this region here where there's 3, so where 3 come together, okay, I could zoom in forever and never find one. And also like here, if I zoom in here, because I don't see this pattern, so I know I'm going to find one here because there's this chiral, it's called chiral symmetry happening right here, but wherever the chiral symmetry isn't, then I will not find one. So here I see this chiral symmetry, so I know when I zoom in on this point, I will eventually find a little Mandelbrot. It might take a while. Oh, I hit the brick wall before I found one. So what's happening here is I ran out of digits of precision of the computer. I literally hit the brick wall. I call it a brick wall because it kind of looks like bricks, okay? My computer ran out of bits. So I ran the measuring stick, i.e. pixel, is too small for my computer to resolve. In order to resolve that, I would need like a special toolkit or more digits of precision. I'd need a special tool or a computer with more digits of precision, like a supercomputer maybe, in order to be able to resolve that. Okay, so that's this version of software. So what I can do with this is I can zoom into a region, I can cycle the palette in order to produce different colors, and then I can generate the image. I can generate a large image and print it, and I can make it any scale I want. So if I wanted to make a giant poster, I could make a giant poster. If I want to, let's say I want to pick more colors, right? I can pick, maybe I want purple. Okay, so now I can pick colors from this color palette. I can replace the colors, so you can see up here is my color palette, so I can replace those colors, and now it's going to use the purple. So, and I can choose colors from, I can load in any picture and choose any colors, and basically the colors determine what the picture will end up looking like. So here I'm going to cycle through the colors again, and sometimes you end up with a series of colors that you really like, and then, oh, that would make a nice poster. So that's what this software is for. This version of software I use for making movies. Okay, so I'm going to reset this, and I pick colors from this color palette because I want to show you what's really happening as I zoom in. So the color, the red, the region where I have red colors here are regions of low iteration. So these are points that take less iterations to reach the escape velocity of the black hole. And so as I zoom in, okay, I'm going to actually pick the palette again, and I'm going to make the colors sort of iterate faster. I think that'll work better. Okay, so now I'm going to zoom in, and you can see that it's mostly red. Okay, then as I zoom in, you start to see the yellow. Okay, so it's taking more iterations to generate that image. And then the orange. Sorry, orange and then yellow. And then the green. So you can see the green is starting to come in. So as I'm zooming into the Mandelbrot set, I'm also zooming across the palette. So eventually you're going to see the blue. purple, and then the pinks. Okay, and you can notice it's getting a little chunky. It's having a little bit of a hard time rendering now because it's taking more iterations to resolve this image. And what's happening is when I zoom in, I'm zooming in to the event horizon. Okay, I'm not zooming in here, I'm not zooming in here, I'm zooming into the event horizon. And the closer I get to the event horizon, the more iterations it takes to resolve the image. And the more details you get as you zoom in. So you can see as I'm zooming in, it's actually filling in more details. I can also spin it. I can spin it to the right. I can spin it to the left, right? And I can make movies with this. So I'll show you how that works. I'm going to reset again. And I'm going to record. I'm going to start recording. Okay, so now I can record my sequences. So you can see I can like make some crazy sort of zooming in videos and put them to music. So all the videos you see on my YouTube channel that are to music, that are fractals to music, were done using this software. And I can like back up. And zoom in to another region. Okay, I'm going to stop that. And I can play it back and scrutinize the sequence. So, and then I can, if I click make movie, it'll turn it into a video animation, which I can later put to music. So, you know, this software is a lot of fun to play with. If anyone's interested, I can give you the executable and you can play with it. It's written for the PC. So if you have a PC, you can play around with this software. It's kind of fun. All right. So now I want to show you. This is my test bed. I call it a test bed because this is where I run all my experiments and run more quantifiable tests. Okay, so here, what I want to show you, here you can see that the Mandelbrot set is really a gradient generator. And what I mean is you can see that it's generating a gradient which gets tighter and tighter and tighter as you get closer to the event horizon. And so this region here are all the points that take one iteration to escape the boundary. So this is the photon sphere boundary. This is the boundary condition, which is 2.0 of the complex plane. So a distance of 2.0 from here is the escape velocity. Okay, so these are all the points that escape after one iteration. These are the points that escape after two iterations, and here are the 2 points. So basically it goes here, then it escapes. And then 3 iterations, you can see, 3 iterations. There's 3 points, 3. 4 iterations, and so on. So why is this important? Why is the fact that this forms a gradient, why is that important? Well, I want to show you something. Everyone's probably seen a topological map, and topological maps are really maps of gradients. Okay, so you can see this is actually a mountain. Okay, and when at the peak of the mountain, the lines are really close together, but where the geometry is flat, you have lines that are really far apart. So the Mandelbrot set, so this is analogous to that, only in reverse, because this is more like a hole than it is a hill. So as the gradient gets closer and closer to this event horizon, and I'll just zoom in on it to give you a closer look, you can see that the topological lines are getting kind of closer and closer together. Okay, and you can also see, let's see here, you can also see that as I get closer to this boundary here, that this pattern over here becomes more complex and I end up with more iterations. So as I get closer to the Mandelbrot set, I get more iterations. And if I go in here, you'll see the numbers go way up. Okay? And then when I cross the boundary, something different happens. Okay, so something different happens in here. Let me zoom out a bit. I just want to show you something different happens in here than it happens in here, and this is the principle of incommensurability. So the points that are in this black hole region behave differently than the points out here. So the points out here always escape the boundary. So even the ones that are really, really, really close to the event horizon, they eventually escape. They eventually escape. Even it might take 20,000 iterations, or it might take 1,000,000. I found some points that were up to 1,000,000 iterations before they escape. Okay, and the points on the inside never escape, and this is what they look like. So here is like this, yeah, so here is like 200 iterations. So this takes 200 iterations before it resolves. Now the inside points resolve differently than the outside points. The outside points resolve by escaping this boundary. The inside points resolve by collapsing to singularity. And what I mean by that is they basically collapse to the end of the digits of precision. So if I run out of digits of precision during the iteration process, then I can guess that that point belongs to the black hole region. And I'm going to show you a little video on that. Okay, I call it a wormhole video. So here we go. Okay, so I want you to pay attention to these points right here. Okay, so these are the starting, this is the point of the beginning. This is this point here. This is the very first point that I selected and then iterated through z equals z squared plus c using the matrix form. Okay, so this is the first point, this is the second iteration, this is the third iteration, this is the fourth iteration, this is the fifth iteration, and so on. And in a static image, you can't really see what's going on. So the image on the right shows what's going on through the iteration process, that the measuring stick is getting smaller and smaller. And if you look at these numbers here, you're going to see the digits of precision locking in as the zoom in process goes on. So here we go. So now we're zooming in, so you can see the digits are stabilizing as we zoom in. And then at the very end, once it runs out of digits of precision, okay, it kind of wiggles a little bit, and then it stops. And basically, I have run out of digits of precision. But if I had more digits, I could zoom in more. Okay, so that's the important thing here, is that the points on the inside behave differently than the points on the outside. The points on the inside are collapsing towards singularity, to collapsing smaller and smaller and smaller and smaller and smaller until they run out of digits. And the points on the outside are the points that eventually escape. And they're morphologically very different. So the points on the outside are kind of messy. They're not very coherent. Okay, see? There's like 39 iterations, and you know, it doesn't really look like anything. The points on the inside, okay, they are more coherent. They look like this one here looks kind of like a spiral galaxy. And you can see as I go around that it spirals. There's, you know, that looks like the spiral arms of a galaxy. So that's really interesting in itself. And you can see as I get closer to the event horizon, if you look at these numbers up here, you see that the numbers are continuously increasing. So it takes more iterations to get to this boundary. And the same thing happens on the outside. It takes more iterations to resolve this boundary. And you can see there's a little bit of fireworks going on when I cross the boundary. Right? You see a little flash. Right? There's 3,635 iterations. There's more than 10,000 iterations. You can see that's a very complex pattern. And if we zoom into that, you're going to see that pattern over and over and over again at every scale. So, you know, this is a really important point. Event horizons are domain separators. I call it a domain separator because it's separating the domain of the collapsing points with the domain of the expanding points. Okay, these points are expanding. The trajectories are expanding until they reach the escape boundary. And if we go back to my paper, okay, let's go back to my paper. I'm going to show you some points that are very close to the event horizon. Okay, so these points here, so each of these trajectories, right, is very similar to one of these astronomical cosmological structures. And so this is what gave me the idea, because these are very difficult to find. These are super, super high iterations, like in the tens of thousands or hundreds of thousands or even a million iterations. Okay, so these are these regions, these points, are super, super, super close to the event horizon. The closer I get, the more complex the morphologies are, and that to me is really interesting. And the fact that these look so much like cosmological objects, they're not exactly the same, but they're very, very, very similar in morphology to the cosmological objects. So it's really hard to believe that the Mandelbrot set just accidentally does this. There must be something to it. Okay, so I want to show you one more thing to do with the Mandelbrot set, and this has to do with the Julia sets. Now, for every point on the complex plane, you get a unique Julia set. Now, the Julia set is specific to the location in the complex plane, right? So each point in the complex plane generates a unique Julia set. Now, here's the interesting thing. The points on the inside create a Julia set with a nucleus, and the points on the outside create a Julia set without a nucleus. They refer to this as a Cantor dust. It's a Cantor dust. It's also referred to as a disconnected set. Okay, so the points on the inside create a Julia set with a connected set, and the outside points create Julia sets that are disconnected sets. Okay, they don't have a nucleus. They behave completely differently. And this is the principle of incommensurability again. The points on the inside behave completely differently than the points on the outside. Just like the points on the inside generate different trajectories than the points on the outside. Okay, the Julia sets are just a rendering technique. Okay, Julia sets are just they use the point on the complex plane is basically hard coded into the whole image, whereas the Mandelbrot set is like the meta set. So the Mandelbrot set is a picture of all the Julia sets. So it contains all the Julia sets. Some people think it's the other way around, but it's not true. The Mandelbrot set is the meta set of all Julia sets. Okay, so you can see each point that I point to makes a different Julia set. And so the Mandelbrot set is kind of a map of all the locations of the Julia set. And by looking at the Mandelbrot set, I can tell which points create a Julia set with a nucleus and a Julia set without a nucleus. And you can see if I go out here, it creates two blobs, right, that are disconnected. And then as I go, as I cross this boundary condition, they come together and form one unit. But then it's got two blobs here. Okay, so as I go into the next iteration, you can see those two blobs come together. And then as I go in, those two blobs come together, and those two blobs come together. And so, you know, this is interesting. I don't really know what this means in terms of magnetism or cosmology, but the fact is that as I get closer to the event horizon, the Julia sets become more complex. So this event horizon is really the key to, I think, understanding event horizons in general. Okay, and I think event horizons in nature are more like this and less like the Schwarzschild black hole, or Schwarzschild event horizon, which is just a sphere or a circle. Okay, again, the points on the inside of the Mandelbrot set create, as I get closer to the event horizon from the inside, the Julia sets also become more and more complex. And as I cross the boundary, so I can zoom in and get much closer. So as I cross the boundary, you see we get much more complexity. And then we get the Cantor, we get the disconnected sets. Okay. So that's pretty much all I wanted to talk about today. I just wanted to show you a couple of versions of my software, and I really want to just sort of put the focus on this event horizon, because I think this is the most interesting thing. And I think event horizons in nature may also have properties that are like this. I hope you enjoyed this video. I felt a bit uncomfortable doing an ad hoc, unscripted video. I hope it comes across okay, and hopefully next time I can get back to the Ken Wheeler's Missing the Secrets of Magnetism. Step out of the frame.